Thank you all for coming. My name is Oscar Johnson. I'm going to be talking today about some work that I've been doing for my dissertation here at Louisiana State University about how long it takes for a species to become sympatric. So first I want to talk about the speciation cycle. What we have here is a hypothetical ancestral species at the top center. And as you progress clockwise around the circle, the populations diverge and then can either merge back into one species via hybridization, or the two species diverge to the point that they can become sympatric, and then the cycle repeats itself. So much work has been done on the speciation process, but rather less has been done on the temporal aspects of the later stages of the cycle. For example, there's evidence that speciation can take as little as 1 to 2 million years in birds. Looking at this in a little bit more of a simplified framework, we have here our ancestral species, which then undergoes speciation. And then following that diverges to the point that the two new species can coexist. So really what we are looking at is what needs to happen after speciation that then allows for the buildup of alpha diversity. Now, this waiting time to sympatry can be mediated by a variety of factors, including interspecific competition, hybridization, competitive exclusion, trait divergence, or just stochastic processes. And much of the work that has been done on this has been in island systems, and rather less has been done in continental systems. First, we need to define a couple of terms. So sympatry refers to species with overlapping geographic distributions. And the degree of sympatric range overlap is calculated as the proportion of the distributions that are overlapping from the perspective of the species with a smaller range size, so 50% in this example. Now, within that area of range overlap, species can be either syntopic or allotopic, which describes the degree to which species co-occur at the same localities in their overlapping distribution. This is usually due to fine scale differences in habitat. Now, if we go out to a given location, for example, here's a typical species list from here in southern Louisiana, we see that the species present tend to be very distantly related. For example, even though I detected 4 species of flycatchers, they're all in different genera. So really what we're asking is what allows for the buildup of alpha diversity, and specifically, how long does that take? So there has been some work that has been done on this topic in continental systems, but the estimates for the times to sympatry vary quite widely. So across a wide swath of bird species, we've got an estimate of about 4 million years for sympatry to establish. But in the suboscine family for Nereidae, one study estimated that it takes much longer, 14.5 million years, but with considerable uncertainty on that estimate. While in European birds, sympatry takes about 2.5 million years, but fine scale syntopy takes considerably longer, up to 6.5 million years, but with very small sample sizes on that study. So you can see that there's quite a bit of variation in the estimates of the time to sympatry. And despite this, we don't have a good understanding of how these transitions to sympatry happen at a really fine scale. So for example, if transitions to sympatry are easier via shifts in habitat, then we would expect transitions to allotopy to be faster. Conversely, if species are, say, diverging in niche within a habitat, then transitions to syntopy might be faster. So these differences in the timing of syntopy versus allotopy have implications for what pathways species are taking to be able to coexist in geographic space, and then how those translate into the buildup of avian communities. So specifically, I'm asking, how long does it take for species to become sympatric? And then does this differ between species that are syntopic and species that are allotopic within that zone of sympatry? Our study system is the suboscine passerines. This is a clade of about 1,300 species with most of the diversity in South America. For this study, I'll be focused on just the continental North and South American radiation of the suboscines. For our sympatry calculations, we obtained range maps from BirdLife International, filtered to the breeding distributions only. And then the fine scale syntopy and allotopy data came from point count style observation data from citizen science programs after a lot of quality control. A recently published species level phylogeny of all the suboscines provides the evolutionary framework for the analysis. So for every pairwise comparison in the phylogeny, we categorized species as allopatric, sympatric, syntopic, or allotopic based on those distributional databases that I just mentioned. So then for each species in the phylogeny, we obtained the divergence time estimate for the closest relative with which it is sympatric. For example, here for Fluvicula pica, we know that it's sympatric with Arundinicola, which gives us our minimum age for sympatry. We also know that it's allopatric with the other two species of Fluvicula, which gives us an upper bound for the time spent in allopatry. And we did this across all species in our data set. So going back to our original schematic, we want to model the transition from speciation on the left to sympatry on the right. And to do this, we use multi-state Markov models, where we're estimating the time to sympatry that happened at some point between our observed sympatry and allopatry divergence times from the phylogeny. And we defined sympatry using 10 different range overlap thresholds from 10% to 100%. So looking at the results, here we have time on the x-axis and different thresholds of range overlap for categorizing species as sympatric on the y. The 20% range overlap has kind of emerged as a standard for assigning two species as sympatric, and our estimated waiting time for that transition to sympatry is 5.7 million years. And notably, the waiting times for more extensive range overlap are considerably longer, so up to 13 million years, indicating that this is a very protracted process overall. So these are just the same plots that I showed you in the previous slide, but divided up by family. So we've got the different sympatry cutoff values color-coded here on the right side of the plot, and the estimated waiting times to sympatry at the 20% range cutoff are listed there on the plot. So we can see that there's quite a bit of variation among families. So in the Tyrannidae and Furnariidae and the Pipridae down here at the bottom, these waiting times are a bit shorter. But in the Rhinocryptidae and the Grallariidae here at the top, the transition to sympatry is much more protracted, up to almost 10 million years, even at just the 20% range overlap threshold. Although it's worth noting that the confidence intervals on those estimates are quite broad due to lower sample sizes in some of those families. Now, if we look at the finer scale co-occurrence data, recall that when species come back into sympatry, they vary in the degree of co-occurrence. So we can illustrate this as a three-state model where the initial sympatric overlap is either syntopic or allotopic. Because we're just looking at the initial transition to sympatry, we assume that this is also a one-way process out of allopatry, and we don't have to calculate the transition rates between syntopy and allotopy. Just to give a sense of what some of these syntopic or allotopic species pairs look like, I've got here one species pair that is syntopic in our data. These are the two species of Fluvicula, both of which are widespread in wetland habitats in South America. In contrast, two species that are allotopic in our data, these are the two Middle American montane Epidinacs. They're broadly sympatric, but one is found in forested habitats while the other is found in edge habitats and marshes. Looking now at the results for just a sympatry threshold of 20%, we can see that there's no difference in the waiting time estimates for syntopy or to allotopy. Both are similar to each other and to the overall estimates for sympatry. And again, if we look at this across all different sympatry definition thresholds, so the blocks between each of the dotted lines, we again see that there's no difference between the syntopy and the allotopy waiting times. So what we're seeing is that the primary source of variation is the degree of sympatry rather than whether species are syntopic or allotopic within that area of sympatry. For this next slide, I'm going to look at only that 20% range overlap threshold, but look at the variation across families. Here we can see that again, there just really isn't much difference in the waiting times for allotopy and syntopy. One thing that does jump out is that the confidence intervals on these allotopy waiting time estimates are extremely broad. And that is entirely driven by very small sample sizes of allotopic comparisons in the data set. That actually in and of itself is quite interesting. So looking at our data, about 80% of sympatric comparisons are syntopic. So while it takes just as long for a species to become syntopic or allotopic, those transitions to sympatry are much more likely to be in syntopy. So that means that most of the buildup of species richness seems to happen between species in similar habitats rather than between habitats. So in short, divergence in habitat association does not explain the timing of the transition to sympatry. So in conclusion, the average waiting time to sympatry is about 5.5 million years, but with variation among families and with the amount of sympatry. We found no difference in the waiting times between syntopy and allotopy, at least in these early stages of sympatry that we're looking at here. But we did find that transitions to syntopy are much more frequent than transitions to allotopy. So I have a lot of people to thank. A lot of institutions, both for funding and for the specimens that are the foundation to all of this work. There's just not enough space to thank all of the institutions here. Quick announcement though, I'll be starting a postdoc this winter at the University of Texas at El Paso in Dr. Mike Harvey's lab, where I'm going to be continuing to work on this topic. And what I presented today is really only scratching the surface of what we can do with this data set. I have a whole lot of trait data that I'm going to be using to look at the role of morphological divergence on the transition to sympatry. So stay tuned on that. And as a side note, Dr. Harvey is recruiting graduate students and a technician, so please spread the word. Thanks for listening.